the paper I'm presenting today, this is a joint work with some other co-authors, Professor Victor Cholodzukov from MIT, and Ivan Freeman is from Boston University, and Chen Huang from University of Bristol. In this paper, we try to propose lasso type estimator for dynamic linear panel models, because the very popular Arellano-Bond estimator, it suffers some bias when the panel is long, when T is large, and we will propose some lasso type instrument selection technique to reduce the bias. So let me begin with a brief introduction about dynamic panel and the AB Arellano-Bond estimator, just in case you are not so familiar with this background. On the left-hand side, YIT is the response or the outcome. And on the right-hand side, we BIT as part of the covariates. That is the policy variable or treatment variable that we are interested to study the effect of BIT on YIT. By the way, panel data, the data are observed across individual I and also over time period T. Dynamic is in the sense that the legs of YIT are also included on the right-hand side. So CIT contains the other covariates or control variables, including the legs of YIT and possible other treatments if you are interested to make inference. And in our application, we will study the effect of screw opening on the COVID spread in the US. Alpha I and gamma T, they are the unobserved unit and time effect. They are random, but essentially in this paper, we treat them as fixed parameters by condition on the realization of them. And the error term, epsilon IT, we assume they have zero mean and constant variance and satisfy the so-called weak sequential isogeneity condition. Or in other words, the covariates are predetermined with respect to the error term. So XIS and epsilon IT, they are uncorrelated for any S less than or this CIT part, I will first talk about the basic model where the dimensionality of CIT is fixed, and then we generalize it to a high dimension model where the number of covariates can be large. The AB estimator, they removed this unobserved effect by transforming the model. And you can take a difference over time and also diminishing at the unit value level to remove the gamma T and alpha I. But since the covariates are only satisfying the weak isogeneity condition, so the transformed model, they will be endogeneity. In particular, theta YIT minus 1 on the right-hand side will be correlated with theta epsilon IT. So when there is an endogeneity in the regression, we have to use some instrumental variable to fix this issue. And they propose to use some internal instrument because the legs are naturally ready to use for this endogeneity problem. For each time period T, all the legs variable XIS S less than or equal to T minus 1. For example, Y for Y until IT minus 2 and the D until IT minus 1, they are all valid instruments to be used for this every regression. The AB estimator is a GMM estimator based on this moment conditions. And of course, it's an over-identified GMM problem, and the bias comes from using too many instruments, because at each time period, you have so many legs that can be used, and the total number of instruments is of order T squared. So there are so many legs, and that is where the bias comes from. But anyhow, this is a very popular empirical method for dynamic panel, and with a very high citation if you check in Google Scholar. And then I will talk about the issue for this bias problem. AB can be biased when the panel is long, so when it's large due to the use of too many moment conditions. This is very well documented in the literature. As I mentioned, the number of moment conditions is of order T squared. The sample size in the panel data will be denoted by small n, capital N times T. The bias the bias scales with m divided by small n, which might not be small compared to the sampling area 1 over root small t. In that case, we will not be able to kill the bias in the expansion, so that will lead to some not robust inference if you want to do some tests on the parameter of interest. In general, this is a problem for GMM estimation with many moment conditions. To establish the approximate normality or consistency of the GMM estimator, we essentially need the so-called small bias condition. That is m squared. M is the number of moment conditions, should be small compared to the sample size, small n. Formally, the ratio of m squared divided by n should be vanishing as m and n tends to infinity. However, in the AB case, m squared is t to the power 4. And if your capital N is not large enough as the cubic of capital T, we are not able to kill the bias. So the small bias condition is not satisfied in this case. And to have a better understanding of the small bias condition, we can have a closer look at this higher order property of the GMM estimator. And as shown in the paper by Newey and Smith, the asymptotic second order, we can make an asymptotic second order expansion of the estimator theta hat around the true. So the leading term is an divided by root n, where an is the well-behaved asymptotic normal term, is big OP1. And the b is the first order bias term, is a big O of n. And Rn contains some higher order remainders. And we expect an dominate B and also an dominate Rn. And to make sure that an divided by root n dominate B divided by n, we need this condition. This is the small bias condition we have seen in the previous slides. And the reason is we want to kill the bias term to say that the leading term dominates the bias term. And to dominate the remainder, there is another condition, but that is relatively weaker than the first condition. Okay, and here I'll make some review on the related literatures. So lasso is known to be a very effective variable selection technique. And using lasso to select moments is not new. For cross-sectional data, the econometric paper by Bernoulli et al., they already studied for linear moments, and later a working paper by Law considered the nonlinear moments. And alternatively, for the GMM with using too many moments, we can consider some kind of regularization on the weighting matrix, because the weighting matrix, optimal weighting matrix is the inverse of the covariance matrix. So when the dimension is high, there might be some issue. And you can do some kind of regularization, and some examples can be the paper by Classical and her co-authors. But I think their work are not very general, so they mainly consider homoscedasticity or one-step GMM estimators, not quite general. And a very recent working paper by Chen et al., we find their estimation procedure quite similar to what we propose. They consider a minimum distance estimator that combines regularization on the weighting matrix and also false fitting. I will comment on false fitting later. But the difference between our work and theirs is they propose a quite general framework that based on some high-level conditions, and we look into a more specific model, and we provide a verification on those high-level conditions. So this is the difference. And some other alternatives to GMM estimator, that is the generalized empirical likelihood. Theoretically, they have some robust property, orthogonality property, saying that they are robust to too many instruments. And in the literature, GEL or penalized GEL by combining with lasso, they have been very well studied for cross-sectional data or time series data. But as far as we know, not to the panel data yet. And also, according to my experience, I feel like GEL, it works pretty well in theory, the very nice property, but for implementation, it's not very easy. The results are very sensitive to initial values or whatever. So that's why we didn't take this direction. We didn't go for this direction. And another related work is the Chen et al. They propose a split sample or jackknife bias correction directly on the AB estimator. That is their device AB estimator for large T. But actually, there is no moment selection, so the estimation is not so effective. And in our simulation study, we compared with their method, and we found that when T is larger, it's still very time consuming and it doesn't really work pretty well. And lastly, the other alternative approach is maybe you want to say, why do you have to remove transform the model to remove the fixed effect? Why don't we just estimate the fixed effect? So for high dimension dynamic panel model with fixed effect, of course, there is an alternative way that you estimate effect model directly. But usually you have to impose some sparsity condition on the fixed effect or some cluster structure condition on the fixed effect. That can be possible, but maybe those assumptions are not relevant in practice. And later I will show you that the sparsity our method relies on that can be verified. So this is the reason why we want to do the AB estimator instead of the fixed effect estimate. And this page, I summarize the main contributions of this paper. We propose a lasso version of AB that makes use of the approximate sparsity structure in the moment conditions. The idea is pretty simple. If the temporal dependency is weak, intuitively, only the recent legs, they are more important relatively. The distance legs are naturally less relevant than the close legs. So there should be some kind of sparsity structure in the moment conditions, and we will make use of this sparsity structure to do lasso in selection. So this idea is pretty easy. And in particular, if you know your data generating process, theoretically, you can verify this sparsity and you do know the level or the order of the sparsity. And then by using lasso in selecting the moments, we will reduce the bias since we use less moment conditions than the original AB estimator. And also we will improve efficiency by the so-called forward orthogonal deviations. That is another way to transform the model. In an early version of our paper, we also do the first differencing as AB. But some referee comments on that if your errors are originally uncorrelated over time, but first differencing will introduce some correlation on the transformed errors because the delta epsilon IT and delta epsilon IT minus 1 share some common terms. The forward orthogonal deviation is there is a weighting scheme behind this. You can imagine GLS. So this weighting scheme will help you to improve efficiency. If your error term originally is uncorrelated over time, then the transformed error by FOD is also uncorrelated. But of course, efficiency is not the main focus of our paper. We didn't really establish any efficiency boundary of our estimator. But what we did is in the literature, the efficiency bound for dynamic panel with fixed effect has been established for some under some certain assumptions like Gaussian ID errors. And we try to show that with this under the same assumptions, our estimator attains the efficiency bound that has been approved in the literature. So that is why we can claim sort of efficiency for our estimate. We didn't show any efficiency results in general setting for our estimate. we know for machine learning method, the overfitting bias is always an issue, and people like to use cross-fitting based on cross-sectional sample splitting to reduce the overfitting bias. And we will also do this in our estimation procedure. The other contribution is the exogenous controls of a high dimension, diverging dimension are also allowed. If time allows, I will also show you an application that will study the effect of screw openings on the pelvic spread interior. By the way, I accept any questions during the talk also. So if you have any questions, you have a question? Okay, all right. And then I will formulate the model and bring you the estimation procedure. So let's first consider the AR1, the basic AR1 dynamic panel model, and later we generalize to high dimension as well. So CIT is a vector of covariance of fixed dimension at this moment, fixed dimension, including YIT minus 1. Transform the model by FOD. This is the weighting scheme. So we subtract ZIT by a future average. And there is a useful weighting scheme of this future average, and that will help you to cancel out some correlation in the transformed error terms. Tilde is the demeaning, cross-sectional demeaning that is used to remove gamma T. Our proposed mass estimator has two steps. The first step is the lasso step. We do moment selection, cross-sectional lasso estimation to select the most useful legs that will be used in the IV regression. And the second step is the IV regression using the predicted instrument from the first step. So I think it would be useful if I go back to the paper, they consider cross-sectional data. Let's see how it works for ID data, and later I will explain how we generalize this from cross-sectional data to panel data. So in the econometrical paper by Bagnoli et al., they consider a regression model with endogeneity. So DI is the one endogenous variable that is the treatment for policy variable, and it's not uncorrelated with the error term. So suppose you have a bunch of instruments at hand, and the dimensionality of the instrument is much larger than the sample size n. And in the reduced form, we can project the endogenous variable DI on the instrument variable on the IV space. And this RID is some kind of linear approximation error that is assumed to be negligible. And they will use lasso on this step to select the most important instrument. So then the theta can be estimated by two steps. The first step using lasso in this projection stage, and then you obtain the optimal instrument DI hat. In the second step, you do a two-step least square regression using DI hat as the instrument to get the final estimator of theta hat. But I want to remark on here, we should do two-step least square regression within the second step. So it's not like these two steps are corresponding to the two-step least square estimation correspondingly. So in total, there should be three steps, and we do two-step least square regression within the second step. Actually, both ways, you can identify the two parameters in the moment conditions, but only this way is in the fashion of optimal instrument, because we will have some kind of Neyman orthogonality condition that the nuisance parameter pi can be partials of. So Neyman orthogonality is a very important thing in device machine learning, because pi is something you have to estimate, but no one is really interested in pi. And we expect to partial it out by some kind of orthogonality condition, and only this way we can have this orthogonal moment condition. Okay. I should comment on the extension from cross-sectional data to panel data. The first extension is now we have panel data, and at each time period, the moment selection might not be the same. So we should do lasso stepwise. For each time period, you select the most important legs. So it's not only using lasso for regression at once, we should do it stepwise for each time period. And in the end, we aggregate the result over T as well, not only over I, but also over T. And secondly, the lasso step relies on some sparsity condition, and they have to impose it directly because there is no natural reason for sparsity in pi. But we do have this natural sparsity because if the temporal dependency is weak, not all the legs are important, and we can verify the sparsity condition in our field. And the third extension is we allow for the inclusion of a high dimension control variable here. So it's a CIT can also be included in the structure model. That is the extensions from their work to our paper. The estimation procedure, the notation may be a little bit heavy, but actually the idea is quite simple. For each time period, we use lasso to select the instrument. So let WIT denote the endogenous variable. After transforming the model, there will be some endogenous variable, and you regress this endogenous variable on the legs. They are a valid instrument, and we do lasso here. Lambda T is the penalty parameter in lasso, and the omega TS are the penalty weights. So this is some kind of adaptive lasso, and we have the penalty weights. And the penalty weights, if you have some prior information about the importance of the legs, you can incorporate them. For example, omega TS can be a non-decreasing function of T minus S. Closer legs, you put more emphasis and so on. Or it can also be used to account for some kind of heteroscedasticity in your model. And then the predicted value are denoted by WIT hat, and that is this is a linear lasso regression, so it's easy to obtain the predicted value. And the second step is a simple IV regression. So it's two-step least squared within the second step. And for panel data, we do the double summation and aggregate over I and also over T. This term, delta X tilde IT hat, is the predicted instrument you obtain from the first step. So I hope the estimation procedure is clear. All right, name orthogonality is the thing to partial out the pi part, because the pi part is the coefficient in the lasso step. We have to estimate them, but we are not really interested to make inference on them. So we want to partial out the effect of them to ensure some kind of robust or valid inference on the parameter of interest. Theta is the parameter of interest, but pi is not the parameter.
The leg is
yes, so AB is you can use the internal instrument. Legs are ready to use as a legs. You don't need any external instrument.
Oh.
And because the instruments are legs, so there is a very natural sparsity thing. So only the close ones are important. Maybe you want to ask, since it's very intuitive that the closer ones are more important, why don't you truncate at some point only use the closer legs, not the others? So we try to verify this sparsity under some certain examples. And for example, if your data generating process is some kind of AR process, it's true that there is a truncated thing. So you can stop at some particular point. But more general, like an ARMA process, or when MA is incorporated, there is a geometric decay, and we don't know where to truncate. And given that lasso is very easy to implement, and why don't you use a data-driven way to select instruments? So that is the reason we prefer to use that. Okay, here let's talk about the overfitting bias. I think nowadays all the double machine learning or device machine learning paper sample splitting is always accompanied there to reduce the overfitting bias. Here we suffer overfitting bias because the same observations are used in the first step and the second step. Therefore, the so-called generated error or the prediction error from the first step might be correlated with the ordinary error, and this correlation will introduce some bias. This is called overfitting bias. And sample splitting is the idea you partition your sample, let's say, two folds, and the auxiliary sample is only used to estimate the nuisance parameter, and the main sample is used to estimate the parameter of interest. Then by conditioning on the auxiliary sample, the estimator of the nuisance parameter is actually fixed. So in the expansion, there is no need to handle this some terms in a very complicated way, like the empirical process, talking about the entropy or of the functional space, because they are fixed. And the high dimensionality comes from this part. Therefore, sample splitting helps to reduce the computation of the rate condition a lot. But there's some new finding in when we work on the revision of the paper. We found that actually FOD helps to decorrelate the errors from the generated error and the ordinary model error, because the FOD transformation, you have seen that there's harmonic weights, and it helps to spreading the transformed error over many future periods. So we find that using FOD or using sample splitting, theoretically we get the same rate. So, but if you use first differencing, then sample splitting, the role is very important. But if you use FOD and actually in large sample splitting is not so crucial as we expected before. But in finite sample, if the sparsity is still quite large relatively to N, then sample splitting definitely helps in some simulation results. So in the literature, sample splitting is used for debiasing device, and as I have explained, it decorrelates the generated error of the selected instrument and the transformed error in the model in the main regression, and it simplified the regularity conditions for asymptotics, and the more important, it opens up the possibility of using other machine learning methods than Lasso. So in this paper, we mainly consider Lasso because sparsity is ready to use, and in this Lasso case, we can verify a lot of things in this specific case. But actually, thanks to sample splitting, the selecting step, any machine learning method, including some nonlinear model, can also be used as long as you have some kind of fast enough consistent rate. So not limited to Lasso. Lasso is only one example we show in this paper. If we, instead of the specific rate condition, we impose some high level condition, then it will also incorporate other machine learning methods. Based on the cross-sectional sample splitting, we will apply a cross-fitting procedure to achieve to make use of the full information. How much time do you have? There's still 30 minutes left for the question. Oh, so on this page, I briefly talk about the procedure for sample splitting. We split the panel in two halves, and we do the splitting cross-sectionally, so over I, not over T. This is an example for 2 folds, but of course you can do 5 folds, and if you have cross-sectional independence, the partition can be random, not necessary to be first half and the second half. The model transformation should be made within each subsample. And for the first step, we should use the half sample A and obtain the predicted values in half sample B. And then the second step is only is the IV regression only based on the subsample B. So the auxiliary sample is used to estimate the nuisance parameter pi, the lasso part, and the main sample is used to estimate theta, the parameters of interest. And then you reverse the rows of 2 half samples and to get another counterpart and average them. That is the sample splitting test. All right, then we can generalize our model to incorporate many exogenous covariates. So in addition to CIT, of course, this high dimension part can be included in CIT, but to make a clear notation, we introduce another notation, X2 IT, that is the high dimension part. And we assume some kind of relatively stronger exogeneity condition that after the model transformation, there is no endogeneity for this X2 IT part. For example, the strictly exogenous variables can be included there. Theta 1 is in dimension B1, theta 2 is in dimension B2, and C1 is fixed, B2 is allowed to be divergent, drawing reason. And here we assume some kind of sparsity in the nuisance part. So this sparsity, unfortunately, we cannot verify. So that is the sparsity in the control variables. So we need it to partial out the effect of it. So in this general model, the moment functions are given as follows. Within the parentheses, that is the transformed model errors, and they are uncorrelated with the instrument. And there are two parts in the instrument. Because X2 IT is the strictly exogenous or strongly exogenous part, so they can be used as the instrument for themselves. So there's no need to look for other instruments. And the UIT is the ideal instrument for the X1 part, and they are the predicted value from the lasso step. So the two components, they construct the instrument for this general model. And how to do the estimation for the general model? Maybe it's better to give you some general idea at this moment. So in the low dimension case, it's easy to partial out the nuisance parameter by some kind of projection that can be exactly done. But in the high dimension case, we cannot exactly make this kind of projection. So we have to do some kind of approximation. And the approximation is done by introducing this weighting matrix. WT can be viewed as some weighting matrix there we select instrument. To partial out theta 2. Theta 2 is a nuisance part we are not interested. So the partial derivative of the moment function with respect to theta 2, we expect it to be 0. And that is this expectation to be 0. But in the high dimension case, maybe unfortunately we cannot get this exactly 0, and we introduce this weighting matrix WT to say after some kind of transformation, you will get a 0. And for the purpose of identification, the X1 part, we assume some kind of full rank condition to make sure that the model can be solved. And this problem can be solved by a Dantzig selector. So we do some kind of regularization on this weighting matrix. So that is what I mean by selecting moments.
I'm so sorry.
Yes.
You said it was okay to interrupt.
Yeah, yes.
You just go back the last time. So that expectation, what's that expectation over?
Okay. So this G is the moment function. We expect this to be 0 when you have the true values of the parameters there, right? And the orthogonality condition is take partial derivative of the moment function with respect to the nuisance parameter evaluated at true. We expect this to be 0. The idea is some kind of local mistakes you make in estimating the nuisance parameters are acceptable. So this part comes from the partial derivative of this G function with respect to theta 2. This is a linear model, so with respect to theta 2, it's just a product of these two. But in the high dimension case, without this WT, it's hard to say this is exactly 0. So we introduce some transformation that helps us to approximate the problem to be feasible. It's okay? So the Dantzig selector, we do some kind of regularization. We minimize the one norm of this matrix, and then the constraints is the X1 part is full rank and the X2 part is 0. So For example, you can take the sub-matrix of identity matrix, and then the conditions are satisfied. And this LT is the tuning parameter in this density selector estimation. And once you obtain this WT hat, the weighting matrix, the final estimation on theta 1 can be obtained by a so-called weighted weighted IV estimator or regularized IV estimator. So compared with the ordinary IV regression, you don't have this W hat, but now they are incorporated as the weight to this is a weighted least-square estimation to approximate the solution for this high dimension case. Because this is high dimension, unfortunately we cannot exactly get the analytical solution. We have to do this kind of approximation. Okay, and then I want to talk about some theoretical results. So let me first show you some key assumptions that we make on the data generating process. Firstly, conditional on the individual and time effect, the covariates xit and the error term epsilon it, they are assumed to be ID over I, and over T xit, they are trained stationary. So since there is no stochastic non-stationarity, and the epsilon it is shown to be stationary over T, but of course conditioning on the individual and time effect. And we use the general dependence measure, the functional dependence measure by Wei Biao Wu to quantify the degree of dependency. I'm not sure if everyone knows this, but due to time limit, I may not be able to go into the details, but it's a very general dependence measure. So it covers a large class of linear or nonlinear time series process. For this paper, we consider the dependence adjust the sub-Gaussian or sub-exponential norm. So of course, we restrict something on the tail. The tail is not flat tail is not really allowed in this case. But you can replace this by some other general finite moment conditions. In some previous papers, we extensively discussed the trade-off between the exponential tail condition or the finite moment condition. So this time we decide to focus on the easy case, only the exponential or sub-Gaussian tail. So we are not so general to the finite moment condition, but it's not hard to replace. So in that case, some more demanding rate condition will be called if you want to have more generality in the moment. So such assumptions are made on covariates, also on the error terms, and in addition, some other conditions on the error terms like MDS over T. This is a very common in dynamic panel because by including enough lags with a rich dynamics, it's reasonable to say there is no real correlation over T. The conditional, we allow for heteroscedasticity, but there is a uniform bound of the conditional variance. That is also not a strong condition. And the other thing is the covariates are predetermined, and we say the degree of predeterminateness is kind of summable with respect to lags. So I think this is also a reasonable assumption. In particular, if this x is the lags of y, and based on some autoregressive model, you can exactly verify this condition. It's not hard to see why it works. So in the theory, we prove two main elements. The first part is the consistency in the lasso step, and then the second component is the asymptotic normality of the second step estimation. So here I introduce some new notation to stack the observations over I. We define the linear projection for the first step. So left-hand side is the endogenous variable, right-hand side instrument. You project the endogenous variable on the IV space, and the pi t zero is the linear projection coefficient, or namely the OLS estimator in population. So that is what we mean by the linear projection coefficient. So far, we don't know any structure on this pi t zero. It can be sparse or it can be not sparse. We don't know anything about it. It can be viewed as our target. And then on top of that, we consider a sparse approximation of this pi t zero, which is denoted by pi t star. And pi t star is the minimizer of this, it's kind of a MSE arrow, so it's the prediction norm is minimized and with respect to some sparsity condition. So that is the sparse approximation. And we quantify this approximation error by this prediction norm. So pi t star and pi t zero, we have some measure to quantify this approximation error. St star is a very important quantity. It characterizes the sparsity of this pi t star, and it is determined by the degree of temporal dependency in the data. I have emphasized this for several times during my talk. And in the paper, we verify that in many certain examples, the element in this OLS estimator in population, it decays geometrically. The decay is governed by the autoregressive coefficient, and therefore it leads to some kind of approximately sparsity structure in the moment condition. So then we can say it makes a lot of sense to consider this approximate sparse approximation to the population parameter. Otherwise, it's maybe you can complain that why you consider approximate sparse approximation, because we can indeed we can verify this sparsity in many certain examples. And if the approximate sparsity is true, we can show the oracle order of the sparsity at t star is of order log n. I don't know how to read this. The minimum between log and t, and accordingly there is an oracle rate of this approximation error. This oracle order of sparsity is much smaller than capital T, so that is why our estimator can reduce the bias compared to AB estimator. And the oracle, the word comes from ST star is the minimizer of the is the optimizer of some kind of risk minimization problem. So there is oracle order for that. So consistency, there are two components. One is the approximation error. The other is the estimation error. But the estimation error is standard. So any Lasso paper has studied the estimation error. That is the deviation between pi t hat and pi t star. That is very well studied in any Lasso paper. So I will probably skip. I will probably go through very fast here. Based on identification conditions and also a properly chosen tuning parameter and penalty weights, then you will have the consistency, the estimation error pi t hat and pi t star is very well controlled. And then by combining approximation error, estimation error together by triangle inequality, we will have the consistency. Consistency is pi t hat is close enough to pi t zero, but we decompose the problem into two parts. Okay, then the more crucial part is the inference theory, the asymptotic normality for our final estimator theta 1 hat.
Sorry, my guess a bit over time.
One more time.
Yeah.
Okay, then maybe I show you the main results. This is already the main results. Okay, then I will conclude this part and then this.
Yeah.
So we have an extension of the estimator around the true, and this is a very standard, and we assume the population, the limit of this matrix is non-singular, so it's invertible, and then through some other expansion, analysis, some rate analysis on the higher order term in the expansion. So thanks to the forward orthogonal transformation, the transformed arrows can be treated approximately to the MDS. So the asymptotic variance is very simple. There is no need to consider any long run variance there. And with sample splitting or without sample splitting, actually the asymptotic normality is exactly the same because we use FOD. If you use first differencing, then the rate condition will be different. And this is the very crucial rate condition of our paper. And if you compare this condition with the original AB estimator, we allow for large T greatly. So we are not so sensitive with a large T in the condition. This page explains the role of sample splitting. That is, we want to correlate the prediction error and the ordinary model error after transformation. And I think I mentioned this before that surprisingly, using FOD and using sample splitting, they contribute in the same direction. So the rate would be the same, but if you use first differencing, then the sample splitting plays a more important. I think I can conclude here the simulation studies are not so interesting.